So with that, I will leave the floor to you, and then thanks again, Alyosha, for being there.
Thank you very much for a generous introduction. And I'm very glad to be here. Unfortunately, virtual. I would love to have been in person, but unfortunately, the travel plans did not allow. But at least this way. And I think maybe this is a good kind of this might be a good lecture to finish the summer school, because this is really I I decided that I'm going to talk about some kind of more general kind of big picture things. And so this might hopefully will tie in a lot of the things that you have been hearing for the last week. Um, and I'll make sure to leave plenty of time at the end for questions. So just make a note of questions, and I'll be very happy to answer them. Okay, so I'm going to talk about data. This is something that I've been passionate about for well, since graduate school for over 20 years, and I I felt maybe that okay, maybe everybody has finally come to the same conclusion that I have a long time ago, which is that data is really one of the most important things for the success in computer vision. But actually, looking at what has been circulating in around here in the Bay Area, in the San Francisco, this is one of the uh, documents that have been circulating around. This is a person who left OpenAI and wrote this long manifesto about, the future. And I'm not gonna. You don't need to read it, because here is a kind of a Wordle summary. It talks about AI and GPT and models and research and compute. And I think what's interesting about write-ups like this, and then there has been many others, is if you look at what it doesn't really talk about, and or doesn't talk about that much. Well, data is actually a word that occurs very, very infrequently in this text. Okay, and so I decided I'm going to talk about data still, because I think even though now people are starting to realize its importance, it might be that they don't realize still how important data is. Okay, especially for visual computing. So because in my view, much of the magic in what is happening right now in computer vision and AI in general, a lot of this magic is because of the data. And hopefully in the next hour, I will convince you of this view. Okay. So let's start uh, with going to Paris. Okay. If you ever go to Paris, you go to the Musée d'Orsay, and in there is hangs one of my favorite Monet paintings, Gare Saint-Lazare. And if you look at the painting, you can really feel like you're in this, you know, 1877 train station, the hustle and the bustle, and there is this steam engine approaching the viewer. It's coming directly at us, and there's the steam coming out, and it's a really evocative, immersive painting, I think. But if you look at the steam engine, and if you look at it more closely, we realize that it's just some splotches of paint on a canvas, and it really looks more like a penguin, maybe, or a bottle stuck in a cooler or something like this, right? Where is the steam engine? Because it's not in the pixels here. Well, the answer is that the steam engine is actually in your hands. And each one of you probably sees a slightly different steam engine depending on, which books about steam engines you read as a child, or maybe it's like steam engine museums or something like this, right? Um, and this is very important to realize how much of what we are seeing is not actually in the world, but is in our memory. Here is another example. This is a very blurry video of by made by my great friend Antonio Tralba, starring Rob Fergus, a famous researcher. He's when he was young. He's working in his office in MIT, and it's a very blurry video, but I think all of us kind of can figure out what Rob is doing here. In fact, we are so good at kind of inferring what is being depicted that actually sometimes we're completely wrong, because here you can see that Rob is actually talking on his shoe, and then he's going to listen to his Coke cans, and then he's going to type in front of a trash can with a stapler, and then there is a printer is actually a toaster. Okay, so actually sometimes our memory plays these funny tricks with us. Okay, and this is because, as Moshe Bar put it, our perception relies on memory as much as it does on incoming information, which blurs the border between perception and cognition. And Lance Williams puts it even more starkly. Mind is largely an emergent property of data. Okay? So, given this, it's interesting to note how, at least in the old days, data did not really get that much respect. Everything was really about algorithms. You focus on algorithms. You write you study algorithms in your classes. If you want to write research papers, it's all about the algorithms, and then maybe you have some features that you give to the algorithms, and then you give them, you run it on some data. But the data is kind of like an afterthought. You really don't really spend that much time on the data. And this kind of a pyramid has has been going on for many decades, and I feel like it's wrong. Okay, and here I'll give you a few kind of historical vignettes to tell you when it has led us astray. So this is probably something that either you heard about in the current last week, or perhaps if you took a computer vision class, you know about face detection. Face detection is really the first real success story of computer vision. It happened in the late 90s, and I was a graduate student back then, and I remember how it was very depressing. Nothing really worked. The whole field, just nothing worked, at least in recognition. And then, boom, there was a bunch of uh, something started happening, and suddenly we were able to detect faces, and then that was like really the first great success story. And perhaps you even have heard of the paper that kind of is credited with being the first paper to really make face detection work. Does uh does anyone know what that paper might be? Maybe you heard it in a computer vision class or something. Okay.
Anyone?
Unfortunately, I cannot hear the
Yeah,
answers.
uh, no one is
No one.
saying that they
Okay.
know. Someone
Okay.
wanna raise hand? No, you have to say it.
Okay. Well,
Too shy.
okay. If you go to the classic textbooks, you will have seen Viola and Jones as the paper. Okay. And that is the paper that's the most famous paper. Um, but actually it wasn't the first paper. Okay. It was actually the third paper. The first paper was actually out of Carnegie Mellon University, done by Rowley, Baluji, and Kanadi. The second paper was also out of Carnegie Mellon University, um, and Viola Jones, the famous one, is the third paper. Now, all three of those papers are actually quite famous. They all got the Test of Time awards, very well respected, lots of citations. But why is it that somehow we, in the textbooks, you only read about the last one, Viola Jones? Was it the best performing? No, actually, Schneiderman Kanadi was the best performing. Rowley Baluji Kanadi was the first. Viola Jones was the first real time, but by that time, Schneiderman Kanadi was also real time. So the reason we remember Viola Jones is because if you look at the first paper, the algorithm that was used was, they used neural networks, which back then in the 90s was this old embarrassing thing that didn't work. So it was not a very sexy algorithm. The same thing for Schneiderman and Kennedy. The algorithm was naive Bayes, which is very, very simplistic, very naive. Viola and Jones, though, had this very cool algorithm called the boosted cascade. And it's an algorithm that I still teach in my machine learning class. It's a very exciting algorithm. And that's really why we remember Viola and Jones. But in truth, all these three papers worked more or less the same. And the reason they all worked has nothing to do with the algorithm at all. What made them work is that these were the first three papers that realized that in addition to the training on positive data, the data that has faces, you also need to give the algorithm some negative data, images that don't have faces. Okay. And these were really the first three papers that made this realization. And that's really what made them work. Okay. And so here, I call it our scientific narcissism, that all things being equal, we prefer to credit our own cleverness, the algorithmic cleverness, as as opposed to crediting the data. Okay, and that I think is fundamentally a dangerous 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 direction. Okay, because really data is the thing that seems to be making a lot of our problems solvable. And there is a wonderful paper. It's very short. It's kind of old. It's from 2009, but it's still, I think, quite interesting, called "The Unreasonable Effectiveness of Data." And the argument that they make in this paper is that, okay, parts of our world can be explained by elegant mathematics, physics, chemistry, astronomy, but some things just cannot be. Psychology, genetics, economics, and AI. Okay. And this is exactly where the magic of data has been very, very helpful. And so, why is this? Well, because these things like psychology and genetics and economics and AI, they are um, kind of driven by evolutionary processes. Physics and chemistry, there's nothing, it has nothing to do about with evolution, right? It's just fundamental laws of the universe. Whereas in things that have to do with evolution, humans, animals, human behavior, they deal with a lot of entropy, a lot of just randomness that exists in all evolution driven organisms, just because there's no reason for it. Just this is just how things happened. Okay. And all of this randomness, you need somewhere to put it, and this is where you need the data to kind of to record and to store this randomness. So let me kind of give you maybe a little bit of an example, what I mean. Let's say that your goal is computer graphics, and you want to make a special effects for some movie, right? For example, you need to create smoke for a movie. Well, in computer graphics, actually, we know how to generate smoke pretty easily. It's been known for 30 years. Okay, you just basically use the Navier-Stokes equation, and you set a few parameters, and then you basically put it in a physical simulator, and you get this beautiful, beautiful smoke. You can see uh, beautiful synthesized smoke that basically does not look any different from real smoke. Okay, great success of computer graphics. Now, but what if instead you need to synthesize, let's say, the bark of this tree, the pattern of bark of this tree? Now, the problem is that we don't have this nice, compact little physical equation. And if we were to write down an equation for this bark, it will require um, knowing maybe the genome of the tree, which is thousands of parameters, maybe the location of the tree, the weather where the tree was growing, whether you had squirrels on this tree or some other animals, right? All of these parameters make some influence on the appearance of that bark on that tree. Okay, and these are very, very hard things to come to model. Okay, and this is where it's much, much easier to just take a lot of pictures of different trees and essentially interpolate between those pictures. So on the left, you have tight little equation that generates a lot of the world. On the right, there is no nice compacted equation because the structure of the tree is very, very data rich. And this is exactly where large data is extremely helpful. Okay. Now, the good news is that, of course, we have not lots and lots of data right now. So that's not an issue. Okay. And so with lots and lots of data, what we are seeing is that even some stupid brain dead lookup, also known as the nearest neighbor classifier in official machine learning lingo, it works surprisingly well. Okay. So here is maybe one of the most important papers in computer vision of the last 20 years. Okay. And you know that it's important because it was rejected from all three major computer vision conferences. This is the tiny 80 million tiny images paper by Taralba, Fergus, and Freeman. Um, and here the authors asked a very interesting question. They said, well, if you take a 5-year-old kid, how many images approximately does a 5-year-old kid seen in his or her life? And basically what they came up with was kind of a rough estimate of about 80 million. Okay. And basically this is a paper that says, okay, let's just, get 80 million images. Now this is 2008. Okay. So disk space was very expensive. And so they decided that they're going to capture those images, making them very small, 32 by 32 pixels. Okay, just because they just didn't have the storage space for large images. But it turned out that even those tiny images were actually very, very, very useful. Maybe you have heard of the CFAR 10 dataset or the CFAR 100 dataset. Well, CFAR 10 dataset is basically a tiny little slither of this 80 million tiny image dataset that the CFAR people decided to extract. Why did they only took 10 categories? I cannot tell you. In fact, I think the CFAR 10 might have slowed progress in computer vision considerably because they somehow didn't think that you needed lots of data. So they made a tiny data set from something that was actually a very, very good, very big data set. Okay. Because what the paper showed is that as you increase the number of images in your data set to 80 million, and then you try to find the nearest images to a particular a query image. So let's say that this is your query image. And these are the top 16 closest images to this query image. You can see that at the level where you have 80 million samples, these images look surprisingly similar to the image here. The same thing for this landscape, the same thing for this lake or river. When you have lots and lots of data, your nearest neighbors start to look very, very similar to the input image. Okay. So similar, in fact, that you can actually reason about a new image like this input image just by looking at the set of closest images, the nearest neighbors to this image in your data set. And then if you have some associated data with those images, for example, in this paper, what they had is they used the word net hierarchy. So you can basically have all of these images vote on the hierarchy, the word net hierarchy. to figure out what is depicted in the simple image. So it's like, and through the votes, you can see this, okay, entity, object, living, organism, person, and then I think it's like a biologist or something like this. So it's actually getting almost correct classification for this image just by essentially nearest neighbor vote on this WordNet attributes. Okay. Now, at the same time, my former student James Hayes and I were uh, interested in a related problem of asking, what if we have an image, we have some foreground that we don't like, okay, we can erase it, that's not hard, but now we have a hole. How do we fill in the hole? And basically what we used is this similar idea of, let's just download a couple of million images and then find the closest image to the image that we have right now, and maybe somehow use this image to fill in the hole with a little bit of computer graphics. And you can see here, it's actually looking pretty good. Okay. Again, the algorithm is very, very simple, basically trivial, but the data allows us to do something like this. And then our follow-up paper was to see, okay, maybe we can also use this to tell something about the image um, using our data set. And in this particular case, what we were interested in is kind of like if you have ever played GeoGuessr. It's kind of like, you know, before GeoGuessr was popular, we had this project called Im2GPS. So basically, given an image, guess where on Earth was this photograph taken. And we basically used a very similar approach. We downloaded this time 6 million images. Now, this is 2008, this was the biggest, by far the biggest data set on computer vision. Okay. And now we basically took the closest images from this 6 million image data set. And then we had them vote because all of those images had a GPS tag associated with them. And we basically let them all vote on a map of the Earth. Okay. And what you can see here is that there is a few images that kind of agree with each other on the location right here. And in fact, that's the correct location. This is somewhere in southern Utah. And in this particular case, we show that it actually we were able to guess the correct location again with a very, very simple nearest neighbor algorithm. Okay. Now, the point of the story is that 15 years later, what happened? Well, the deep learning revolution happened. And some folks at Google decided that they're going to kind of follow up on this problem of guessing the geolocation of an image, but using a deep network. Okay. And so they basically put in a deep net, and they also, of course, because they're Google, they had much more data. Okay. And their performance was much better. Okay. Now, luckily, this paper was sent to me to review, and I noticed that here they're changing two things at once. Can you see this? Right? They're basically changing the algorithm from nearest neighbors to a deep net, but they're also changing the amount of data from 6 million images to 90 million images. Okay. So which of those two changes actually uh, produce the improvement in performance? We don't know. So I asked this question to the authors, and they ran an experiment where they basically did an apples to apples comparison. They used their deep network, but on the original 6 million image data set. And what we found was that actually their method on the same amount of data as what we had was not better than our old method at all. In fact, for some regimes, their performance was slightly worse. Okay. So what we're seeing here again is the same story that when we think about the improvement, we immediately think about it's the algorithm's fault. But actually, in this case, again, what we are seeing is no, it's actually the data that's doing the heavy lifting. Now, you can say, wait, so, neural networks don't really need it. We don't need neural networks. We can just do nearest neighbors now. We can throw away all these neural networks. No, that's not what I'm saying. Neural networks are very, very powerful, and they're also much, much faster than nearest neighbors. But I think the point here is that the powerful neural network actually did not need to work that hard in this particular case, because really all the cleverness was in the data. Okay. And so it's important to note that that in it's good it's good to try to separate the contribution of the data versus the contribution of the algorithm. In this case, it was clearly that the data was doing all the heavy lifting. Okay. So the good news is that you can have very stupid algorithms, but lots of data, and you get to this unreasonable effectiveness. Okay. But then often people tell me, wait a minute, but this doesn't really explain, human vision, because surely humans cannot remember, millions and millions of images, right? Impossible. Well, actually, interestingly enough, we have some evidence to show that humans are very good. They have very high capacity for visual memory. Okay. And this is a series of works by a wonderful researcher from MIT, Odd Oliver. And she ran a set of experiments on measuring the human visual, the capacity of the human visual memory. In fact, there is some old work in 1970s that already showed that humans were really good at remembering many, many images. So in this work by Standing, they showed that given 10,000 images, people were able to remember 83% of those images, which astonishing, right? But the problem was it wasn't quite clear how much people remembered, because all of these images that Standing was showing were quite different. One was maybe ocean, the other was forest, the third one was savanna. So it wasn't clear if they were remembering maybe just a few keywords, or maybe just a few objects, or what were they remembering, really kind of a detailed representation of the image. We didn't know. And so this is what Odd and her team decided to experiment with. Okay. And so what they decided to experiment with is remembering images. Sometimes they are very, very different, like different categories. So, objects of different categories, but also trying to make it a little bit harder and saying, okay, it's the same category. They're both peppers, but, different instances of this category. Or they thought, okay, we can make it even harder by making it the same instance, but a different state of the objects. So here, the goblet fell down, and here it's standing up. Okay. And so basically they presented lots and lots of images this way to the observers, and they had two tasks. One task was basically to note when an image has been presented for a second time, and second, after the experiment was done, to tell which images they have seen and which images they have not seen. And the results of this experiment were really astonishing. In fact, they were so astonishing that I thought that would be actually good to do a mini version of this experiment for you guys, so you can really feel invested in the outcome. Okay. So this is going to be the interactive part of the talk.
All right.
And the idea is we are going to show you lots of images. And then at the end, we're going to ask you which ones you have seen and which ones you have not seen. Okay, so every time you see an image that you have already seen before, you're going to clap. Okay, is that a plan? Okay, so
Is that okay?
we're
It's okay. The
yeah.
microphone is on.
Okay,
Ready.
so the images are going to be very fast. They're going to come in very fast, so you have to pay attention. Okay, and we're going to do this for maybe 5 minutes or so. Okay, so are we ready? Okay, here we go.
Yes. No.
Okay, so I actually haven't heard the clapping, so I don't know how
Oh,
well you guys
they,
did.
they were clapping. Sorry, like a lot of
Yeah.
clapping at different times. Sorry, the
Okay,
microphone were on, but yeah.
I see. But how good were the claps compared to the
Uh,
correct?
I don't want to. I don't want to say who was wrong or not, but there's some people
Okay,
did a few
okay,
mistakes. Let's say.
okay. Yeah, but notice, a few mistakes. Okay, let's try.
Yeah,
Let's
a lot
try.
of good answer. A lot of good
Yeah.
answer.
Okay, now let's ask what Odd asked people at the end. So this, and imagine this is after 6 hours. Okay, 5.5 hours of doing this nonstop. This is very tiring thing. Okay, which one did you see, A or B?
People
Because
answered A. Majority is A.
okay, that is correct. What about this, A or B?
A. Majority
Okay,
A.
what about this, A or B?
B.
Very good.
They,
Okay,
disagreement. Give us a minute. What's
okay,
happening? Okay, people say B.
okay. Well, basically this is consistent with what they found in their evaluation set. Okay, so the first thing that they found was that for different objects, the memory performance was even better than standing. It was 92%. Okay, so basically people were able to remember 92% of the instant of the different object categories. Okay, but I think the more surprising was that if you look at the harder tasks, like for example, this two different um, two different remote controls on the TV, or the two different states of the object, people were just a little bit worse, 88% and 87%. Okay, so this basically tells us that we can remember a lot of visual information. Okay, which is maybe not very intuitive to us, because if in terms of words, for example, we can't remember that much. In fact, if I give you a series of random words, you will remember on average about seven plus or minus two. Okay, But for visual data, it seems like we can remember a lot more. Okay. So this is good evidence that actually humans have have a very good capacity for visual memory. Okay. Okay. So this hopefully convinced you that just using lots of data and very simple algorithms might be very effective. Okay. Now, this is kind of the bad news, though. And the bad news is that these kind of raw memorization approaches, like the nearest neighbor methods, they're great, but they have trouble with rare events, what's called the long tail of the distribution. So these are the common things, and these are the rare things. And the problem is that this long tail, it's also heavy. So a lot of the rare things, there exist a lot of rare things. And so this is a very lots of the data is actually in this kind of a rare regime. And if you're doing something like nearest neighbor, well, it's very unlikely that you will just have similar examples that you have already seen if those things are very, very rare. And this is where the modern generative models come into the scene, because they seem to be very, very good at interpolating and composing data from different sources. Things like stable diffusion, DALI, etc. Okay. What do I mean by that? For example, they can generate things like this dolphin in an astronaut suit. Okay. Now, this is nothing that they have seen at training time, right? This There is no dolphins in astronaut suits, you know, uh, in the outer space in any of the real data, right? So this is clearly some way that these methods are composing different pieces of data that they do have in novel ways, right? And this is very exciting. This level of compositionality is extremely exciting. Okay. But you know, maybe again we are getting too excited about the different methods, the amazing algorithms like DALI or stable diffusion, and the fancy language features, and again maybe forgetting about the common element, which is the data. And here is an example of what I mean. So I'm looking at text to image generating programs like stable diffusion or DALI. So I give them a prompt: squirrel reaching for a nut. And these are three resulting images. Okay. And you can see that actually all three are doing a reasonable job. Maybe you like one more than the other, but all three are doing okay. And the interesting thing here is actually these three images come from three extremely different algorithms. So the first one is a diffusion-based algorithm, stable diffusion. Second one is autoregressive, the PAR-T. It's basically like a large language model, but for pixels. And the third one is GAN based, and this is again a very, very different algorithm. Okay. Now, you don't need to know the details of these algorithms, but the point here is that they're all extremely different algorithms, very, very different formulations, ideas, intuitions, everything's completely different. But the results are actually, all results are pretty good. Why? Well, my feeling is it's really because all of them are trained on huge amounts of data, about 5 billion images, billion with a B. So this is a really huge amounts of data. Okay. So it could be that it's not really the specifics of any one particular algorithm, but the data that they're being trained on. And in fact, my former student Taysam Park produced this graph here that I like a lot, which is on the x-axis is the model capacity of different models. So this is DALI is here, Imagen is here, GigaGAN is here, etc. And on the y-axis is the visual quality. So the lower the metric, the better the quality is of the images. And what you can see here is that actually it's a pretty nice linear relationship between the capacity of the model and how good it is. The larger the capacity, which is the more parameters the model has to absorb the data, the larger the capacity, the more data it can absorb, the better the results. Okay. So if we believe this graph, basically the argument is it doesn't matter what the algorithm was used to generate the images. As long as the model has enough capacity, it's going to do well. And the bigger the capacity, the more data it's able to absorb, the better it's going to work. Okay. And this is kind of an interesting interesting point. But still, um, you know, it's kind of magical, right? And it's even magical to me. Like you can give these text to image models a prompt, something kind of fantastical, like a green creature made of leaves and vines bursting out of the ground, ready to attack, right? And you give it to, stable diffusion, and you get something like this. Okay. And it feels very magical. It feels like, wow, it's really able to take some piece of text and really synthesize something kind of novel and creative. Right? It seems very, very magical. Okay. Well, it is magical, but it might be that it's not as magical as it looks from it first. Because here, what we did here is, this is our paper from last year, is we basically said, if you looking at a generated image, we asked the question of what can we find images in the training set, the real images that most influence the appearance of this generated image. Okay, so this is called visual attribution algorithm. Okay, data attribution. So basically, which of the training images attributed the most to the appearance of the generated image. And I'm not going to tell you how this algorithm works. It's actually not that important. I think the more important thing is look at these 6 images. These are the most influential real images to generate the synthetic image. And I think to me, what's striking was that, these real images are actually, well, first, they're not so real. So, okay, one thing that we found out is actually in this real image data set, there is a lot of things that look like painting or things like this, right? But also that they're actually, quite similar. Now, it's still kind of cool. This is still, a different image than any of those. So it's not doing nearest neighbor for sure. But it might be using some sort of interpolation, something maybe as simple as linear interpolation between those set of images, real images, to get us to the synthetic image. Okay. So it's still magical, but maybe it's not as magical as we first thought. So here I like to paraphrase Arthur C. Clarke, that interpolation in sufficiently high dimensional space might be indistinguishable from magic. Something that looks very magical might actually be just a simple interpolation in some space that's very high dimensional. And one example I want to show is something that is actually from 30 years ago. In the 90s, there was a lot of excitement based on this idea of modeling faces as linear combinations of the training faces. So basically, they get, a few hundred face images. Okay. And then they basically, what they showed is that with simple linear interpolation, something that you read about in linear algebra class, just linear interpolation between those, say, 200 faces, you are able to create any other face. Okay? So any face, your face, my face, any face of any human can be approximated surprisingly well as basically a weighted sum of these 200 faces. Okay? And this is kind of magical, right? But it was definitely, and this is a famous paper from Blantz and Vetter, where he showed that basically you just walk in that linear space and you can just create anyone. And so this is kind of suggests that there are more people on Earth than there are faces, right? Because maybe you know maybe the space is not really as rich and huge as we thought. And so to give you a little bit of of a of a of a kind of a feel for maybe some of the more recent stuff that I've been doing. This is a paper that we're just put on archive. Um, so you can think about data set of images, right? Like these old face linear interpolations. You could also think about data set of latent vectors, something like a GAN, style GAN latent vectors. But you can also think of other data sets. And so in this particular work, what we decided to do is have a data set of models. So every model, like a text to image model, has a set of weights associated with it. And we can come up with a set of many, many such models, thousands, hundreds of thousands models, and see what can we learn from a data set of models. Okay, and so this is the paper we're just published. And what we found is that, let's say that you have a model that generates a particular person in different configurations. What we show is that actually just linearly interpolating between the weights of a set of these models, you can generate a new model without any training. This is just linear combination, just linear algebra. You can generate a new model that will produce pictures of a novel person, in this case of me. So I wasn't in any of the training models or training images, but basically it was able to generate a new model that would produce pictures of me. Okay. And so here is a little bit of a details about this algorithm. So basically we started from stable diffusion model, and then we fine-tuned it for a particular person. So we basically have a data set of different celebrities, and we basically created a special model for a given person. And we have about 60,000 such models. So basically, we took 60,000 people and we made one model for a specific person. And so now we have a data set. And this is a data set of these models. Okay, so we have 60,000 of these diffusion models. Each one is able to create one person. Okay, now we can have a linear subspace of weights of all these models. Okay, and now this space, we can do various things in that space. For example, we can basically we can sample new models, right? By just interpolating in that space, we can create new models without any training. For example, say, okay, this is a new model, and this model produces pictures of this person. And this person, we have never seen this person before. This person is never in any of the training data. And here we can create new identities, new models that produce different people. And just to show you that they're completely new, these are the nearest neighbor faces from the training set, and you can see that they're quite different from what we have here. Okay, or we can do editing. For example, we can look at all the models that have mustaches and all the models that don't have mustaches. And this particular model doesn't have a mustache, but now we can basically, or beard, I guess, mustache and beard. In this particular case, we can basically move this representation towards having a beard. And the same model now, boom, it's now generating pictures of a person with that beard. So again, there is no training, there is no backpropagation, there is nothing at all like that, but just by interpolating between the models, you can get this. Okay. Or you can invert a novel image into the space by basically finding a linear interpolation of the existing models to explain this new image. Okay. Now, this is the closest model to this image. And because this image is a painting, you will not get something that is perfect. Oops, sorry. But what you will get is you'll get basically something that looks like a photograph of a woman in this painting. And this model creates different images of this particular person. Okay, and here you can have more examples of this. So here is what happens if you give it a sketch. And here, when sometimes they say that people with pets, they look like their pets. So we decided to test if this was true, and give this picture of a dog, and then project it onto the manifold of faces, and it gave us this person as the the closest human to represent this dog. Okay. And we could also apply this to other things like dogs. Okay. So I think, let's see, what time is it? Yeah. So this gives you a few examples of how powerful the data is. And maybe if we think about the types of machine learning that have been particularly successful, lately it's been these LLMs, large language models, right? They have been working really well, but also they have been using the largest data that we have, text data. Text data is by far the largest data available. Okay. Now, the second most successful approaches have been these image synthesis approaches. And the image data is the second largest data available. Okay. Then we can look at something like video generation, something like Sora. And Sora and video generations in general, not doing so great. And also, we don't have that much video data. And then the stuff that really hasn't worked at all is robotics. Why? Well, because robotics basically has no data. Okay, so you can see that the availability of data can really predict performance on particular tasks. Okay, and this kind of explains this concept of Moravec's paradox. So this guy Moravec came up with this paradox actually all the way in the 80s. And the paradox is basically can be stated as, in AI, the hard things are easy, while the easy things are hard. So the classic example of this is, here is a picture of Garry Kasparov losing to a computer Deep Blue at chess. Okay, this is 1998 or 7, I think. So this has been 30 years ago that computer won against the world chess champion. Okay, so that's a very, very hard thing to do, to play chess. Okay. And computers were able to beat humans. But notice this dude here. What is this dude doing? This dude is basically moving the pieces. Okay. Which basically any kid could do this. And if you look at computers playing humans again right now, there's still no robot that can move the pieces on a chessboard reliably. Okay, so 30 years later, after we have beat, well, after computers have beat humans at chess, we still don't have a robot to move the chess pieces. This is a classic example of the Moravec's paradox. Okay, and basically what we are seeing here is that this is still the case, that the fancy schmancy hard things, we're seeing AI systems doing very well. But the easy things, for example, this is a very new paper just out a week ago that showed that none of those fancy schmancy methods like GPT-4o or Gemini or Sonnet are very good at very simple visual tasks. For example, this task here is how many times does the blue and red lines intersect, right? And here are some examples. And none of these approaches really do very well for this very, very simple task, even though they do so well for the complicated tasks, okay? And basically, to me, the answer is that somehow we ended up in a situation where the, the complicated tasks we have lots of data for, but the simple tasks somehow not so much. So going forward, the text data is the biggest data we have. But guess what? We're almost done with the text data, right? All of these methods, they're basically using, 2000 years worth of human culture. They're reading books, literature, science that have been created by us for 2000 years or more. And they're basically at the end. They basically consume pretty much everything. Now there is only the stupid teenagers on Twitter and whatever, TikTok and Instagram, right? Which is not a very good quality data. Okay. So my prediction is that the text-based approaches are going to saturate because they basically ran out of data. Whereas data, something like visual data, images, video, as well as robotics data, we don't have that much of this data right now, but there is essentially an infinite supply of it, right? Because you can always get more images. You just walk around and just take more images or take more videos, right? And this is definitely not a very good not very high quality data. It's a much weaker data, but there is much, much more of it. So my prediction is that we are going to see more focus on large models that deal with low-level signal, images, video, robotic data, other sensory modalities, things like this going forward, right? And we know that this is actually what happened evolutionarily, right? So in the in evolution, the Cambrian explosion is where most animals started to see and move. So they started to get sensors, and they can also, actuate those sensors, right? And then later, much later, we started to have things like tools and bipedal locomotion, opposite thumbs, hands, and basically, 10 minutes ago, evolutionary speaking, is when we got language and abstract thinking and symbolics. Okay. And so it's reasonable to think that maybe what we should do is we should start from the basic stuff, from from very simple things, and only later get to language. So instead of this kind of top-down approaches that we are doing right now, where we start with language and then try to explain everything with language, it might be that the right direction is bottom-up. You start with low-level physical sensors, pixels, sounds, touch, robot torques, and then you go up. And so that's what I feel is perhaps the more uh, promising direction going forward. And of course, for that, computer vision is very nicely positioned to take advantage of all this data. Okay, so I think I will end here. Thank you very much, and I'm very happy to answer questions.
Amazing talk. Thanks a lot, Alyosha. I know that the remote setup doesn't allow you to feel the atmosphere in the room. There were a number of reactions during the your full keynote, so that was really great. Thanks a lot. I know that people were asking for questions, so this is time. There is one there already.
Okay, let me see if I can get to see everyone. Okay, yes.
Thank you very much for your talk, Alyosha. So I have a bit of question. I think a question, a discussion. So here, so there's a slide. You said the visual space isn't so huge, and
perhaps I don't know. That's just
perhaps I find it counterintuitive with the ideas that all we need is data, because if visual space is so so huge, it means we don't need huge data. We can just compress things to fundamental level and just building things up from there. For example, when it's colors, we only need RGB and we can make whatever other colors from that, right? So maybe we don't need much data. We need to reduce things to a way that we can. So everything is computation, is not memory.
Right.
Yeah.
So yeah. So basically, I guess the argument there I was trying to make is, originally I did not believe in generative models because I thought the visual world is too huge. It's too vast. And just representing everything in the visual world will never work.
Yes.
Basically, you need infinite amount of data for that.
Yeah.
Right?
Yeah.
And I think the success of the generative models and some of these kind of examples from the past, these linear combination examples, suggest that the visual world, while big and very data hungry, it's not crazy big. So I'm not the distinction I'm trying to make is not between big and small. The distinction is between really crazy big and just plain normal big. Right? So like impossibly big versus actually we can do something about it big.
So how do you compare with that with texture world?
With text world?
Texture world.
Oh, texture.
Yes.
Like you mean like the visual texture or like text?
Yeah, so texture. Because also it seems also from the text point of view, each language is a finite number of words, and we can compute everything from there.
Right.
Yeah.
Yeah, let me think about it. Yeah, how?
I'm trying to say maybe we don't need much data. We only need to reduce things to a way we can compute from there.
Right. No. Yeah. I think we need lots of data. I think we definitely need lots of data for any of them, right? But like, is it impossible amounts of data, or is it possible? So what we are seeing for the image, like text to image programs, is, Lion is about 5 billion images, and it's already basically starting to work, right? So now 5 billion is a lot of data, right? It's an amount of data that no human has ever seen in their lifetime. So that's still a huge amount of data. But 5 billion is actually maybe like 1% of all the images on the internet. So in that sense, it's actually not that big. Right?
Yeah, I see.
So I think in that sense, it might be that for visual data, maybe we don't need as much as for text data, because I think in text, you don't need that much to sound like a convincing high school student, right?
Yeah.
You don't need that much to sound like a convincing 5-year-old, but to sound like a convincing professor, you probably need some more, right? So there's like more things to go, like a larger runway. So you can do something reasonable with not that much data relatively, but really, if you want to sound very, very good, you need more, right?
Thank you.
On image, can I just jump in on image, on visual data? What would be kind of the ballpark of order of magnitude missing, in your opinion? Like, are you talking 2 digits, 3 digits, 5 digits of order of magnitude?
Well, I think for images, I think these 5 billion images seems to be maybe enough. I think it's for video. So video is we don't have enough data for video for sure. And Sora is okay. Sora is quite impressive. This is actually done by 2 of my former PhD students, but it's still not great. And I think the reason why it's not great is because we don't have that many good video data as we have image data. Okay, and also video data it's much more bulky, right? So if you have a video, the video is, let's say you have a 5-minute video, 5 minutes, that's 60 seconds in a minute and 30 frames in a second, right? So it's a lot of images, but those images are very correlated. So it's not the same as that many images. So I would say like a 5-minute video is maybe equivalent to like 10 images, right? But it's much, much bigger. So that's a kind of fundamental problem, that videos are not so information dense as images, okay? And so they're much harder to deal with. So video data sets.
What about the quality of data in corner cases that you discuss in your talk?
Yeah. I mean, the same thing. In video data, the quality is not as good as with image data. It's video data is harder to capture. There is a lot of just not good video data. In images, there is a lot of good photographers taking good pictures. Videography is harder, and there's much more crap. So yeah, it's a lower quality data, and there is much less of it. So it's just bad in all senses.
I was thinking quality in terms of distribution, but I think
and also
distribution on the word and cultural
yes,
and
yes. Videos are more like, there is a lot of videos that is just like a dude talking, right? That's not very exciting, right? So yeah, no, basically in all the axes, videos are worse than images at this point in terms of data. Yeah. And there are efforts to make it better. For example, these egocentric data sets of creating videos, putting cameras on foreheads and just walking around. And that's, I think, that's a good direction. But we are nowhere near getting there. Yeah.
All right. I think there are other questions. Yes.
Thank you so much for the talk. There is actually a big need for images, yes, but we don't really hear much about how we can acquire those images, what kind of images are required, and some of data governance type of structures to actually govern or make sure that there's data available that is acquired in the right way for research.
Well, there is various various ways that, well, okay, there is two sides of this. One side is as a researcher, how can you get data as a researcher? And there are standard data sets available, like, for example, the Lion data set is basically just crawls the web and just puts together this 5 billion images. There are other ones that are available, but a lot of that data is kind of junky. Some of it is not great, and it's very, very noisy. And of course, the alternative is just going and collecting the data yourself, and this is of course much harder because of the scales. As kind of from the other point of view, as the creator of data, for example, I am a photographer and I like to take pictures and I like to post pictures. And because I am also a computer vision scientist, I feel like, okay, since I'm using all of these images, I should also give back to the community. So all of my photographs, when I upload them, I host my photographs on Flickr, which is a kind of a photo sharing website for photographers. And there you're allowed to specify the kind of the permissions for your particular photograph, like the kind of what kind of what kind of copyright or rights that you associate with the photographs. And basically I set them all to be what's called Creative Commons license, which means anyone can use my photographs for anything. Okay. And there is actually a lot of photographers that do that. They basically give their photos to the world under this Creative Commons license. So that's one way to kind of have a sustainable way of generating data. Another way, of course, is to somehow have a marketplace where some people will create images and then others will pay for those images. Like, data costs money, so why not just have producers of data and then consumers of data, and then have some sort of a exchange, so that you can it's kind of just any other product, right? I think this might happen in the future. I think right now it's not quite, this kind of marketplace is not quite developed. And I mean, you can have things like Getty Images, for example, or images for newspapers and stuff like this. But I think maybe in the future this will happen, and maybe the methods like with this data attribution method that we developed, that can tell you, for example, you submit your images to some big repository, and then if, let's say, DALL-E or Stable Diffusion use your image to create a synthetic image, maybe then you get paid a few cents or something every time your image is being used in the production of a new image, right? So I think there, there are mechanisms to make this into kind of a marketplace, but I think for that we really need to kind of understand this data influence better, and we are only starting to do this. But I think this is definitely something kind of going forward, right? To see if we can think of data producers just like any other kind of producers. Like it's a product, data is a product. We have people producing the data, and then we have people consuming the data. And a marketplace is when they come together and kind of negotiate for this exchange. I mean, this is kind of a grand future that maybe will happen, but a lot of practical issues will need to get solved before that actually happens.
Another question.
Yes, thanks for the great talk. What do you see as the trend for having better and cleaner image data on the internet? Because that's really the most affordable way for getting images for research.
Yeah. Yeah, I think the trend is not great. In fact, I think the trend is things are getting worse because a lot of the images on the internet now are actually not even real. They're synthetic images. So now we are going into this loop where a lot of the images that people put online are not real images. And if we train on these synthetic images, that's not going to be good, because then we are going to kind of, it's kind of like a perpetual motion machine where we're going to be chasing our own tail, right? And so I think now we have to be even more careful to make sure that we don't train on synthetic data. Luckily, at this point, detecting if an image is real or synthesized is not that hard. So I think this is something that we'll have to start doing. But in general, it's a big problem. It's a big problem. And it might be that at some point we'll just need to start, collecting our own data somehow and not rely on the internet. If the internet gets too polluted, we'll just have to have our own repositories somehow that are, that serve the data. But yeah, no, I think data is it's where the power is, and this is where the kind of the smarts are, and so yeah, we'll have to think of ways to get it in good quality and good quantity. I think for images, things are okay. I think for video, things are really, really bad, and I'm not quite sure how to get them better, except for just really going out into the field and just creating our own data. Like, for example, giving people cameras to wear and just recording them for, in mass. Something like, for example, the Ego 4D project has been doing, right? If you are interested in kind of a really powerful, large-scale data collection effort, Ego 4D is quite impressive. So there might be we'll have to do more of that.
All right. Is there another question? I see a couple. Yeah. Yeah, go on.
Thanks a lot for your talk. I was thinking about explainable AI, and that being somehow opposed to this view of mapping to a high-dimensional space where it's only linear interpolation. Do you have any thoughts on this? Is it a lost cause as we go in increasing dimensions? Or yeah, what are your thoughts on explaining AI?
Yeah, I mean, there is good and bad. So the like things that, for example, that I showed about this data attribution, in some sense that you can think of that as explainable AI, right? That you're saying, okay, here is a generated image. Can I explain which real images most contributed to this image? Like, that's a type of an explanation. Okay. If something could be explained as a linear combination of your training data, that's another type of explanation. It's a very data-centric explanation, and that I think is very cool and very valuable. And I think we should think more and work more in that direction. The kind of but often explainable AI, people mean by it is like, okay, give me a simple explanation of why the network made this decision. Okay. And I'm skeptical that this makes sense. Okay. In the same way as I'm not sure that even humans can really explain their reasoning. And in fact, when we ask humans to explain their reasoning, they just lie. And there's plenty of evidence to show that, a human is making a decision, and then as an explanation of how they arrived in this decision, what they are doing is completely different from their original thought process. Okay, so that you compare what people say and maybe their brain activity or their eye gaze, eye saccade patterns, and they just don't match. So if you have read the very important book called The Thinking Fast and Thinking Slow, it seems like a lot of human decision happens in this thinking fast in system 1, whereas the explanation comes from system 2. And the explanation sometimes actually does not correspond to what the human actually did. I think neural networks are kind of in the same way. And so a lot of this work on explainability is basically making up stories that don't actually have anything to do with how the network actually solved the problem. Okay. And, maybe those stories are useful sometimes, but I worry about us believing those stories too much because, go ahead.
They're very inspiring. Though I think we humans, then we build libraries. We have science to try to get to the end. Do you think neural networks will be able to do something like this by themselves, or is it just nearest neighbor interpolation?
Okay. This is interesting that we could say we humans have science. Very, very small number of us humans have science. Most humans don't use science. And in fact, even scientists, most of the time, we don't use science. You're not trying to optimize every aspect of your life. You make a decision, do I take a bus or do I walk? Okay, you can actually try to calculate exactly which is the most efficient route, or you just, you feel like walking today. Okay. And so I feel like a lot, the kind of using science, this is a very, very rare thing. Most of the time we are just, we make decisions based on, thousands of factors. And so do the computers, right? And in fact, in computer, you can, it's perfectly explainable because it's a deterministic machine. So if you know the input and you know the network, you know exactly what's going to happen. It's perfectly repeatable. It's just too high dimensional for us to understand, right? It's explainable, but it's not understandable to a human. So in a sense, explainability to me almost seems like a perceptual problem. Like the computer knows perfectly well what it's doing. It's that it needs to explain it to the puny human, and the puny human can only hold 7 things in their memory at once, so they just cannot grasp the complexity of the world. So yeah, it's an interesting question. But would the computers, would these models be able to kind of do high level reasoning, prove theorems and things like this? Perhaps at some point. I haven't seen anything like this as of yet. As of yet, everything I have seen is some sort of interpolation between things that are already known. I have not seen an algorithm, prove a theorem that has not been proven before, for example, right? But that might happen in the future. We'll see.
Thanks a lot.
Yeah, another question here.
It's not a question. It's an addition to what you've been saying. So what if explainability is the way of validating what human understand produced by the machines?
Okay, sorry, I missed it. Say again.
I said, what if explainability, what we do, trying to debug what the models are producing, is the way of validating what we understand from our perspective?
Yeah, maybe. I mean, so I think what you're saying is maybe by looking at how computers solve problems, it might tell us more, give us more intuition about how we humans solve problems. Because we too are machines, and sometimes we make decisions that are not explainable. You talk to any psychologist, and they will show you all these examples when humans make completely unexplainable decisions. So I guess you can say, we can observe the computers, and maybe this will give us a little bit more intuition about us humans. I think this is very interesting and very fruitful direction. In fact, I think already what we are seeing is a lot of the kind of failure modes of large language models, for example, kind of reminds us of failure modes of humans. For example, I notice myself, if I read a book and that I really like, then the next week when I'm writing emails, I write them in the style of that book I just read. So this book is influencing my writing style without me even knowing. And that's kind of interesting and maybe unexpected, that how much influence kind of the recent data has on me. So it might be, I think it's a kind of an interesting direction to see if AI can explain human psychology. Yeah, kind of neat,
All right.
neat direction.
Maybe you can tackle one last question. Let's see. Yes.
Thank you for the great talk. My question is not like technical nor philosophical. So I just want to ask for your advice to PhD students who are interested in working on generic computer vision tasks, right? So it looks like it doesn't matter like how creative or novel the technique is. At the end of the day, if you have this extra, like this massive amount of data, it's gonna win. So because these generic tasks, the tech giants are also interested in, it's very difficult to compete with them, right? So what is your advice to such PhD students who are interested to work on such research topics?
Okay, so I don't want to sound so depressing. I think it's not that whoever has the most data win. I think there's still plenty of space for creativity, for intuition, for the flights of fancy. It's not like it's just data. It's more like if you don't have enough data nothing else is going to matter because you're just going to be underpowered. You know, if you come to a car race on a bicycle, doesn't matter how amazing your bicycle is, you're going to lose. So there is basically, data is necessary, but it's not sufficient. Okay. So we need to start at the level where we have a model that has enough data, and then we can do the cool research, the cool intuitions, etc., etc. Now, does this mean we all need to train these ginormous models? Maybe not. A lot of this work that we are doing right now is we take existing models like Stable Diffusion, already pre-trained, and then we fine tune them a little bit, like the work I showed on this weights to waste, this linear interpolation, right? We didn't train the Stable Diffusion from scratch. We fine tuned them, which was actually not that much compute, right? Or, for example, something like Duster. Duster is a great method that has been trained on lots and lots of data, but now you can take that pre-trained model and then maybe you can do something else with it. So I think there's still a lot of exciting things one can do with taking those large models and then putting them together, combining them, fine-tuning them, etc., etc. But I think that the days where you started from scratch maybe are over. Like, you need to start with something that already has seen a lot of data. But we're lucky that we have a lot of models out there in public domain that already have seen a lot of data. And so, the right way, I think, is to start using those models and then build on top of them, or build something using this condensed data that's already sitting in those models. Because lots of data doesn't mean you have to go and look at all of these images yourself or all of these videos yourself. Lots of data could be the weights of a network that has seen a lot of data. That's kind of the entropy is still in there, even if it's in the setting of weights of a network as opposed to actual pixels. So yeah, I wouldn't be so depressed. I think things are looking up for computer vision. When I started, nothing worked, and that was depressing. Nothing worked at all. Now, a lot of things are working, and yes, a lot of those things require huge compute, but there is plenty of things to do, which maybe just one or a few GPUs is enough. So I think there's kind of lots of exciting directions that weren't available to us before, because now things are starting to work. You just have to be a little bit kind of mindful about making sure that you have a little bit of compute and you have some models that have seen a lot of data. Yeah.
All right. There is people asking for other questions, so I'll take at least one. Sorry,
Sure.
Someone that didn't ask.
No worries.
We'll use you a bit more.
No worries.
Yeah, I want to ask a very simple question. Where does your obsession for neural nearest neighbors start? Because I hear you say CNNs are convolutional nearest neighbors, so I want to hear more about.
Well, I mean, okay, that sometimes I just troll people. No, I mean, CNNs definitely can do much more than nearest neighbors, but I think it's, as I showed earlier, sometimes all they do is nearest neighbors because that's really the most important thing. I actually, yeah, I remember playing around with things like even I was reading about Shannon and his work on n-grams in generating English text by n-grams back in middle school, and I thought, wow, just by looking at pairs of triplets of words in a big book, you can generate something that sounds like English. That's amazing, right? I mean, that's basically the basis of GPT, is essentially this Shannon's n-gram trick, which is basically just nearest neighbors, right? So it always kind of amazed me that you can get such good performance with such a stupid algorithm, which suggests that the smarts are not in the algorithm in this case, but the smarts are in the data. And then, of course, in college, I learned about the Cover and Hart theorem, which showed that actually, if you look at infinite data, and all the other things, nearest neighbor is the best algorithm you can get, right? It's basically it's closest to Bayes' risk of all the machine learning algorithms. So it's actually the best you can do, really. Now, of course, in reality, we never have infinite data, so you have to do something smarter. But it seems like it's a very nice baseline. And my favorite pastime when I go to conferences is I go to a random poster and I just ask them, so have you compared to a nearest neighbor baseline? And they, of course, usually they fluster, so, oh, that's a great idea. Oh, yes. And the reason I do this is because what we have seen for the last 20 years is that the nearest neighbor baseline, it's a pretty strong baseline. Now, it might not be the best thing you can do, but it's often the second best thing you can do. Okay. So this is always kind of like a way, like a sanity check. Sanity check to understand the performance you're getting. Is you're getting it because of the data, or you're getting it because of the algorithm? If the nearest neighbor approach works well, that means you're getting it because of the data. And that's important to know. That's something that you need to know.
Great. That was really nice to have all this time for the question. Thanks for extending the slot also. I think it's almost midnight on your side of the planet, right?
Almost, yes. But
yeah, I know also you flew from Europe today, so
yes,
all the jet lag and everything.
Yeah.
Right. So thanks a lot, Alyosha, for being there with us. It was really a pleasure. Let's give him a round of applause, please.
I'm very happy to be there. Sorry that it couldn't be in person, but yeah, great questions, and enjoy this the end of the summer school, and hopefully I'll
only
see you
one day remaining, and it's only the first edition, so there will be other opportunities.
All right. Okay.
Have a great day. Good night.
Take care. Bye.
Bye.